but still present. Okay. So the procedure that we are going to discuss is the following. For every field involved in our formulation, we will consider these two hypotheses. Moreover, we will play with the dimensionless formulation of the problem, assuming suitable order of magnitude of the different dimensionless numbers involved in the formulation with respect to epsilon. So if you remember yesterday, we have seen that in the Stokes problem, the only parameter, the only dimensionless parameter was this m tilde, mu tilde, that we considered to be of order epsilon square. So this is an hypothesis. And so we wrote it as epsilon square mu. And then we have to put all these informations together, all the whole information that we have taken into account should be considered in order to state now the problem to be solved starting from the original equation. So yesterday we stopped here after this technical this evaluation, this technical calculation that we did to have a general form of the gradient of phi epsilon, of the divergence of phi epsilon, and of the Laplacian of phi epsilon. Why we did that? Because we have in mind that we have to manipulate this set of equations where we have the Laplacian and the gradient and the divergence. Okay, so we have to know how to play with these objects. Okay, and so now let's go. Let's do what we have to do. So the point is now, if you let's keep this, and we'll show you the details of this calculation just to let you understand this. So now we have to exploit these conditions for the Laplacian of V and the gradient of V. So the Laplacian of V epsilon will be what? Will be, according to this way of writing things, will be 1 by epsilon, the Laplacian y of V naught. So we are considering V as V, which is considered V epsilon of x as a V of x and y, say V naught of x and y plus epsilon V1 and so on. Okay. So Laplacian of V epsilon will be 1 by epsilon, the Laplacian y of V naught plus so term of order, sorry, epsilon square, plus 1 by epsilon, then the divergence y of the gradient x of V naught, yes, plus the divergence x of the gradient y of V naught, plus the Laplacian y of V1, and then other terms. I don't put the others. Okay. Similarly, for the gradient of P epsilon, so I'm thinking of the different terms involved there. We exploit just this form, so 1 by epsilon gradient y of P naught plus epsilon to the power 0, so 1 gradient x of P naught plus gradient y of P1 plus other terms. Okay, so I took this one and the one with k, this is k, yeah? With k equal to 1, and then there will be the k equal to 2 and so on. Okay, So now we have to, and sorry, that is the divergence of V, which appears here, which obviously will have the same behavior as the gradient. So 1 by epsilon divergence y of V naught plus divergence x of V naught plus divergence y of V1, etc. So these are the three quantities appearing in our original equations that we have that we have expanded, and now we have to manipulate. Okay, so let's start from the first equation. So the first equation is that one. I remember you, this is the balance of force, no? Conservation of momentum, as you prefer. So for conservation of momentum, gives us what? So we have epsilon square mu. I remember you that now this mu is of order 1, no? Because we have written we have imposed the condition that u tilde was of order epsilon square, writing this as epsilon square mu. So epsilon square mu, and then the Laplacian of V, which is this. So it is 1 by epsilon square Laplacian y of V naught plus epsilon square mu 1 by epsilon gradient y, sorry, divergence y of gradient x V naught plus gradient divergence x gradient y of V naught plus Laplacian y of V1 plus minus, sorry, the gradient of pressure. So the gradient of pressure is this, 1 by epsilon gradient y of P naught minus gradient x of P naught plus gradient y of P1 and other things equals 0. So this is the conservation of momentum, and the balance of mass, conservation of mass, just is this, in fact. So it's useless to rewrite, it's just this. Is divergence equal 0. Okay, is this equal 0. Okay.
I cannot read this. I cannot read this.
Conservation of mass.
Oh, mass.
Mass. It's very high. Divergence of equals 0 is the mass conservation.
Professor, you're saying divergence of y gradient of x, but then you're writing,
Divergence?
like when you said it, you wrote divergence y gradient of x, but you're writing the gradient y gradient x.
No. Sorry, because I used a mixed notation. Probably you are not familiar with this. When you write the divergence can be written either like that, divergence of V, or like that with a dot. So let's use the same notation. So this is a divergence of Y. When you see this dot, divergence is okay. It's just a matter of notation. Okay, so now let's try to understand what to do. So if you look at this equation of to the conservation of momentum, we can simplify. So epsilon squared and epsilon squared simplifies. This simplifying with that. And so what can we notice here? We notice that there is a leading order term, which is the leading order term of this equation. Leading order term with respect to epsilon. The highest term with respect to epsilon is what?
First one.
No. This is of order epsilon to the power 0. No? But there is something else which is stronger. This is an order epsilon. Huh? This is of order 1 by epsilon. So this is stronger than that. Huh? When epsilon tends to 0. So this is the strongest term. Okay. Then there is the one which is less stronger than that, but not so bad, which is the one of order 1, which is this, but not just this, also that. And then other terms, this is of order epsilon. Okay? So the idea is that these terms, as they are multiplied by different powers of epsilon, they behave completely independent one from the other. So the point is that you have to solve separately the problem at order 1 by epsilon, and then the problem at order epsilon to the power 0, and then the problem at epsilon of order epsilon to the power 1, and so on. So you have not just one problem to solve, but a cascade of problems. Okay. So let's, this I can cancel, but the divergence at theta. And the same here, this is the strongest one, and then we have that. Huh? Okay. So the first problem that we have to solve is this: gradient y of p naught equal 0. This is the strongest condition to be solved. Huh? Then we have the other problem, which is mu Laplacian y of v naught minus gradient x of p naught minus gradient y of p1 equals 0. Obviously, this is the first problem to solve. Okay. And this we solve independently of the other, because it just involves p naught. We are saying gradient y of p naught equals 0. Then we have this equation. Obviously, this involves p naught, the unknown p naught, involves p1, but we have also to consider that the divergence y of v naught equals 0. Now, what is the consequence of the first condition? It's quite trivial. If gradient y of p naught is 0, this means that p naught no, why no pressure? If the gradient of something is 0, it means that this quantity doesn't depend on what? The gradient y of p naught is 0, it means that p naught doesn't depend on y. P naught doesn't depend on y. So p naught is just a function of x. No? I remember you that how every field, we said at the beginning, every field is a function of x and y. So here we are stating that P naught, the gradient y of P naught is 0. So P naught doesn't depend on y, it just depends on x. So you should start recognizing something. This P naught is a pressure that doesn't depend on the microscale variable. So it is what? It is what we have called previously, in our previous discussion, the macroscopic scale pressure. And what we are interested in fact, in the following problem, is to solve the Laplacian y of V naught minus the gradient y of P1 and the divergence y of V naught equals 0 when there is this force. This is, at this level, this is considered as a known term. So at this level here, the unknowns are V naught and P1, assuming that the gradient x of P naught is given. So this is exactly the same problem that we have solved before, if you remember, when we wrote the Laplacian of V minus gradient of P equal to alpha. That alpha is nothing else than the gradient x of P naught. Okay, so what we are stating here is a problem. Notice that is a problem involving, in terms of derivatives, just derivatives with respect to the y variable. You see that you have a Laplacian y, a gradient y, and a divergence y. You have also the gradient x of P naught, but you consider this object as your loading. Okay? So you have the first problem telling you P naught is a constant with respect to y. So it's a purely macroscopic quantity. It's just a function of x. So assuming this gradient x of V naught given, you can solve the problem in terms of V naught and P1 as a function of y, but keeping any possible dependency on x. So you don't care at this level of what happens at the macroscopic scale. You are just solving the problem at the microscopic scale, where you have periodicity. So we are solving exactly the same problem that we have solved in the last few weeks, but considering now the fact that the variable that we are solving the problem is the local one. And then once you have got the homogenized version of the problem, our field still remains a function of x. So we have removed that unpleasant situation of having, once passed to the homogenized version of the problem, a constant velocity, because the velocity remains a field of the macroscopic variable x. Okay, so what we are stating here is exactly the same problem that we have written before. So this one is exactly the same Stokes problem that we have initially used to get estimates of the permeability via the channel, etc. solution, and exactly the same problem that we have numerically solved the last two classes. So it is this one with the condition, obviously, that V is y periodic. V naught and P1 are y periodic. So this problem is a problem defined on the cell, on the unit cell, with respect to the y coordinate, and we have to guarantee that on the boundary of the unit cell we have periodicity of V naught and P1 with respect to the y variable. The x variable we don't care at all. Okay. So in the end, this, as it is a linear problem, this is a linear problem, no? It's a PDE, it's a system of PDE, linear partial differential equations, and consequently the solution of the problem, as we said already. So this discussion we have not to redo all the details because it's exactly the same that we already did. So the solution, as previously said, will be linear in what? In the loading gradient x of P naught. Exactly as we said a few days ago when we wrote that the velocity of z is a linear function of alpha. Alpha is a gradient x of P naught. Okay. So the idea is that we can consider gradient x of P naught as I wrote it like that, gradient x of P naught ej P naught comma j, and consequently, as we did numerically, we can solve just problems with a unit gradient of pressure along x direction, along y direction, and eventually along z direction if we are in 3D. No? In such a way, then to later calculate the permeability. So the local problem that is written here is exactly the problem that we solved a few days ago, where the W, J, the pi J are the velocity and the pressure, so the P naught and the P1, due to a gradient of P naught along the J direction. So this Wj that you find here in the local problem, Wj, is the velocity V naught due to gradient x of P naught equal to Ej. And pi j is the pressure P1 due to gradient x of P naught equal to J. Okay. This would mean that the final velocity, the global velocity, the V naught, would be a Wj P naught comma J. Obviously, the complete solution. Okay, and the same for P1. The same for P1. Okay. So this problem here is exactly the same problem that we have solved, for instance, that I have shown you the solution in the Python script. So this is the local, we solved in the previous formulation, but we can think of it also as the solution of this problem, because here, in fact, you don't care at all of the dependency of V naught on x at this level, because the problem is stated with respect to the y variable. Okay. So the gradient x of P naught is a loading, exactly as it was before. It was what we call the macroscopic gradient of pressure. Okay. So all what we said about the solution of the problem on the unit cell can be adapted, can be copied, in fact, to the solution of this local problem, with the advantage that now the velocity field V naught would be this linear combination. So let's be more specific. Wj of y times p naught comma j of x. The dependency on x stays here, dependency on y stays there. So the field that we get is a function of x and y. Okay. Before we didn't write this way. Okay. So what comes out from this solution, from the solution of this problem, are these two quantities. It's not that completely finished now, because so this is what okay, so this I wrote with 1 by mu because yes, because the problem, in fact, I should put a mu here. Here there was the mu. So this has been solved. So I incorporated the mu inside the W, if you want. So I put a minus and yes, I wrote with this minus delta Ej, so there is a minus in front of you. So the local problem has been written in such a way that this is minus 1 the minus comes from the fact that if you look at that, this goes with a plus on the right hand side, no? But here I'm putting a minus. So as if I was considering gradient x of p naught either equal to minus ej, not equal to ej. Okay. It's the same, but it's due to the fact that I have in mind what is the final target, say the Darcy law, which would be written as minus k the gradient of pressure, V equal minus k the gradient of pressure. So I want to recover that structure. Otherwise, the minus will be incorporated into the permeability, and I don't write this. Okay. And the mu is due to the fact that here, in fact, I should put a mu here. Okay. So this is the form of the velocity, and now I can calculate the average of this. The average over the domain omega, the whole set, exactly what we did in the code. No? If you remember, yesterday I told you the velocity, the average velocity is 1 by omega, the integral over omega f of v, of v minor. So in this case, the average velocity will be a function of x, because our domain is a domain, our local domain is a domain with respect to y value. Is the unit cell. The unit cell is with respect to the y value. So this is the average of x of v naught of x and y. This symbol means just integral over omega f multiplied by 1 by omega. And so you will get what we are expecting. So you integrate this VI naught, so you put the W, the minus 1 by mu, the W, Ij of y times P naught comma j, and so this guy here in the middle is what? Is nothing else the intrinsic permeability. No? The target is that what we are going to obtain is a relation between the average of x, which is the minus of k by mu, the gradient x, the gradient of P naught. So at this level, everything is completely macroscopic. This is a field function of x, this is a field function of x. So we are purely macroscopic and we got the Darcy law. This is the intrinsic permeability. So it's exactly the same deduction that we did till yesterday, but now on the basis of a field V naught of x and y, of which we are calculating the average with respect to y, and so the dependency on x remains. Notice that if we don't say anything special, this k, as it's the average of wj is a constant, the k, the kappa. Because it's the integral of a function of y over a domain defined with respect to the y variable. It could be also a function of x if instead of considering a purely periodic domain, we introduce this hypothesis of quasi-periodicity. No? Because in that case, you have that your domain omega f depends on x. So depending on the position of the cell, the domain depends on the position. You have an inclusion more or less of more or less large size. Okay, so, but if you keep strict periodicity, your intrinsic permeability will be constant, but this doesn't mean that the velocity and the gradient of pressure are obliged to be constant, because the field that you are averaging is a function of x and y, and the P naught can be considered as a function of x. Okay, so we recover exactly the Darcy law. And this is not the only thing that we recover. Why? Because we have, it was written here, it is, I can take from there. Yes, we have this equation that we can still use. So we use these three for the moment. We use that one, gradient y of P naught equals 0, and we recover that P naught is a constant with respect to y. We use these two equations, so divergence. No, we didn't use for the moment this, and we didn't use for the moment that. We just used this. Sorry, we use this. So we use these two to solve our problem. Yes, this one. No? So the two red equations are these two with respect to y, and that allow us to construct the local problem. We can still use somehow this condition here, which was the divergence y of V1 plus the divergence x of V naught equals 0. Okay, I write it here, just on the side. So we have this condition here that we can exploit. How can we exploit it? So one first result is this. The second result will be that what we can take that equation and we can calculate the average of it in the unit cell. So the idea is that we can take this equation and we integrate it over omega f divided by omega. Okay, So this integration is with respect to the y variable. Okay. Omega f is the fluid part of the unit cell. So we have to treat separately these two divergences. First term is the divergence x of V naught. In reality, they are the second one. So the average of the divergence x of V naught is what? In fact, the divergence x is not affected by this integral, because this integral is with respect to the y variable. So the two operators, divergence x and integral over omega f, which is a y integral, can commute. So you can write this term here, the integral over omega f, this is a dv, dvy. The integral over omega f of divergence x of V naught can be rewritten as the divergence x of the integral over omega f, 1 by omega, of V naught. But this we know that it is the average velocity by definition. So this is nothing else than the divergence x of the average velocity, which is a function of x. And so we can calculate the divergence of the next field, of a field depending on x. No?
So I'm sorry, could you
Yes.
just repeat why the divergence came out again? I'm sorry, I got it.
Because this is a divergence with respect to the macroscopic variable. This integral, this omega f, is the domain, the fluid domain within the unit cell. So this is a domain in the y variable. I put here y just to underline this point. No? So in fact, you are doing this, and you have your periodic domain. You are extracting, for instance, this cell. You take it here, and here you have your y variable. Okay. So here, this is the omega f, and this is the omega. So with respect to this cell, you have all your periodicity conditions that we already discussed. And then at the macroscopic level, you have the variability with respect to x. So this divergence doesn't care about the fact that you are integrating at the level of the unit cell. And so you can invert the two operations, and you can recognize that this object is nothing else our average velocity. So one term of this average, of the average of this equation, is the divergence x of the average. The other one is 0. The other one is 0. Why? Because you have the integral over omega f y of divergence y of v1. This first term here. And this one, obviously, you can dvy. This you can apply the divergence theorem. So you go to the boundary of v1 dot n dsI y. And for this guy, we know what we can say. No? If we think of our problem, for instance, in all other problems is the same. On the external boundary, the part of the boundary where we have periodicity, the V1 is periodic, the normal is anti-periodic, and so when you integrate, when you sum the contribution of V1 dot n on corresponding parts of the boundary, you get 0, no? Because the normal here is like that, and here is like this, but the velocity here is like that, and here is exactly the same. And the same here on the other side. So the contribution of the external boundary is 0. The contribution of the internal boundary, if there is some internal boundary, is 0, because we have the no-slip condition. And so this term is here. And so the result is that we have the classical problem of the classical Darcy problem of the macroscopic continuum theory. The velocity is proportional to the gradient of pressure via the hydraulic conductivity kappa by nu, or the intrinsic permeability kappa divided by the viscosity, and this average velocity field verifies divergence of velocity equal 0, which is the macroscopic scale balance of mass. Okay, so we got the classical version of the problem, of the Darcy problem, where we consider a velocity field which is stationary, which doesn't depend on time. Okay. If you think of the macroscopic problem, this is exactly what we wrote in the course of Porous Media, considering that the balance of mass is simplified because the density is constant, considered as considering the fluid as incompressible, and the velocity doesn't depend on time. Okay. So in the end, what we got with this complete formulation of the problem based on double scale homogenization is that we can construct a solution on a unit cell which gives us the dependency of the velocity and the pressure with respect to the microscale variable, and with respect to this microscale variable, our fields are periodic, and then calculating averages, we arrive at the microscopic relation between the microscopic velocity and the microscopic gradient of pressure, and the equation that this microscopic velocity should verify. So we have completely stated the macroscopic problem. Obviously, this doesn't take into account the deformability of the schedule because we never introduced it. No? That is a purely, we start from a purely Stokes problem, so a fluid problem, and we got this problem here that can be now solved at the macroscopic scale level because you have just fields depending on x. So you put this into the divergence, you get the Laplacian of P. You solve the Laplacian of P, the classical Laplace equation, you find the pressure, and you go back into the velocity and you find the velocity. Okay. But the most important part of this process is the fact that you are able to solve the problem at the microscopic scale. All the discussion that we already had, till yesterday. So the fact that you can solve the problem at the microscopic scale, that this solution provides you via these averages the permeability, and so we get the technical definition of how to evaluate the macroscopic constitutive parameter kappa in terms of microscale of solution of the microscale problems. Then, with this argument, we just removed the condition that at the beginning we had, that the velocity must be constant everywhere, because we have split the dependency of the velocity on the position into a dependency on a macroscale variable and a microscale variable, requiring just periodicity with respect to the microscale one. Okay. So this is the technique that we can use not only for deducing the Darcy law, but for plenty of other problems. And you have seen during the summer school a certain number of applications of that. So what I'm going to show you now is how you can use this technique also to obtain view moduli of the boromechanical model. I think that with François Mignolet you have seen a similar thing, but not based on this technique, but based on averages procedure. You have found, I think, the bio coefficients. So you are going to see this how to get the bio equations and how to define the bio moduli by this alternative process. Okay. Okay. So this is the last item, periodic homogenization of saturated deformable porous media. So first of all, we start from just a porous medium but empty. Okay, so we start from simplest thing and then we complexify. So consider that what you are going to see also with Patrice Cartreau after the break will be an application of these techniques to essentially beam theory. Okay, so this technique can be used for plenty of applications. Either because, as we are doing here, you assume that because of the separation of scales, essentially your domain is will provide a response very similar to the one obtained from a periodic medium, or because you design your structure to be periodic. For instance, when you have seen also with Angela Amadeo, you in MS Square, the metamaterials. Metamaterials are objects like that, are cellular objects which are reproduced with this human cell, which is reproduced plenty of times. So it's exactly this. Then the point is at what level you want to investigate the behavior of those objects. But somehow you should focus also not only on the macroscopic behavior, but also who is giving you the microscopic properties. The microscopic properties should come from the microscopic scale analysis via this kind of homogenization method, or other methods as you want. There are plenty of homogenization techniques that one can use. But in any case, wherever you have a periodic structure, you have the interest in upscaling information from a detailed into a coarse description. Okay, so this is now the case of porous media, our old friends. In particular, we start with an empty object. So essentially, the point is what we are expecting with respect to a purely solid material is that the fact that it is the object we are playing with is porous will modify the mechanical properties of our average medium. No? So we should expect staying in linear elasticity, that what is relevant will be a Young modulus and the Poisson ratio or the two Lamé moduli, but of the homogenized object, which would not coincide with the moduli of the particles. Okay, so what are the equations that we need to play with? The equations are obviously the usual ones of classical continuum mechanics. So divergence of sigma equals 0. Sigma, and put here sigma s because now we are focusing on the behavior of the solid. Here, this is just an empty space. So divergence of sigma is equal 0, so I do not consider bulk force, I just consider eventual attractions or applied displacements. So divergence of sigma equals 0 in omega s. I assume that as this is an empty space, the boundary condition on all the internal part, all the interface between what is called here omega f, but there is no fluid in fact, and the solid is, the condition is zero traction. No? When you have a free boundary, the free boundary has zero traction. Do you agree with it? I also. Okay, so this boundary, there is just atmospheric pressure. We don't consider the atmospheric pressure, so it's zero for us. So this is free of charge. So on gamma, the interface, sigma n equals 0. Then the constitutive relation between sigma and this E is the gradient, the symmetric part of the gradient of displacement as usual. It's classical linear elasticity. Nothing special, but defined over this this cell. And so our unknown is U, obviously. The displacement, and we isolate. So you see that this domain is periodic. So this cell is reproduced plenty of times in this domain. Okay. So this is our candidate to be the unit cell. So where we can define the y variable, and we will consider our unknown US to be y periodic over this cell. Okay.
Why is the attraction not the pressure? Why is it 0 instead of the pressure? Can you say that again?
Because it's empty.
It's not saturated.
No, it's an empty. For the moment, it's an empty porous fluid.
Oh.
Then we will put the fluid later. For the moment, it's just an empty spherical. Okay, so there is air inside, and we consider air as zero pressure. Okay. On the other hand, when we will put in the gate the fluid, obviously there will be the pressure of the fluid. But here, for the moment, there is nothing, so zero traction. So exactly as we did in the previous analysis, we consider our original field U of epsilon and x as a U of x and y, and considering once again y as x by epsilon, exactly the same process, nothing different, and we introduce this asymptotic expansion of U. So once again, US will be U naught of x and y plus epsilon of U1 of x and y plus epsilon square of U2 of x and y, and so on. And all the derivatives, so the gradient and then the divergence and so on, will follow this relation. The gradient is the gradient x plus 1 by y gradient y, as we wrote before. I wrote before with the field. Okay. So we have to now to use this condition for the gradient and consequently for the divergence and this expansion in this set of equations. So obviously the governing equation of this problem you know very well because you have seen plenty of times now. The governing equation of this problem, how is it obtained? Replacing the formula of strain into the constitutive relation and the constitutive relation into the balance of force, in such a way that you have a set of PDE, of 3 PDE, 2 PDE if you are into E, into the unknowns which are the components of the displacement. So this is what we are going to do. So let's try to do step by step. So we have gradient of u, which we said is gradient x of u plus 1 by epsilon gradient y of u, but u is expanded as u naught plus u naught of x and y plus epsilon u1 of x and y and so on. So this means that we have to replace everywhere this expansion. So we have gradient x of u naught plus 1 by epsilon gradient y of u naught plus epsilon gradient x of u1 plus 1 by epsilon gradient y of u1 and so on. No? Okay. So the symmetric part obviously will, so just to confirm, you have the higher order term, the highest order term, which is 1 by epsilon gradient y of u naught, plus gradient x of u naught plus gradient y of u1, which are the terms of order epsilon to the power 0, and then the other terms. Okay. So the symmetric part, so what I call here E, the epsilon, the strain, I don't use epsilon because otherwise it's a mixture of a symbol. So the E epsilon is 1 by 2 gradient u epsilon plus gradient u epsilon transpose. And so you will have a 1 by epsilon, so the highest order term will be what is called here Ey of u naught. So let's write it like that. Gradient y of u naught plus gradient y of u naught transpose by 2. This is called Ey of u naught plus 1 by 2 gradient x of u naught plus gradient x of u naught transpose, which is the Ex of u naught, I think that is. And then you have also 1/2 gradient y of u1 plus gradient y of u1 transpose, which will be Ey of u1. Okay, so we indicate with Ey and Ex the fact that the symmetric part of the gradient is calculated either with respect to the y variable or with respect to the x variable. Okay, so the E epsilon in the end plus additional terms is just 1 by epsilon Ey of u naught plus Ex of u naught plus Ey of u1. Okay. Okay, just the symmetric part of this, nothing special. What is considered here? So obviously, what I should do, what I should have done at the very beginning, would have been the same argument to develop, the same argument as we did before entering in the asymptotic expansion for the Stokes problem. So making the problem dimensionless. So in principle, this version of the problem is already the dimensionless one. So consider that this equation is not dimensionless, no? Because this is stress divided by length, no? Divergence of sigma. So this is force by meter to the power 3. No? But obviously you can introduce a reference pressure, a reference length, and made everything dimensionless. So this would make dimensionless A, the stiffness. No? Should I write this explicitly? So you have divergence of sigma s equals 0. You write sigma s as, let's say, p bar by L square sigma s tilde. No? Your sigma s was A E of US. Obviously, E is by itself dimensionless because it's the symmetric part of the gradient of displacement. So, gradient of displacement is length, the displacement divided by a length, the gradient. So, ES is dimensionless. So, if you write it like that, P tilde by L square equal A, so sigma tilde equal A E of US, you can multiply everything by L squared by P bar, and you get sigma S tilde equal to so this guy is now dimensionless. You call it A tilde. This object can be rewritten as a E tilde of U tilde, no? In the sense that it doesn't change anything because you assume that US is L US tilde, but the gradient is 1 by L, the gradient tilde, and so in the end you will get E tilde of U tilde. So the same relation that we wrote here, we can rewrite with tildes. And then you say, okay, forget about tildes and I can write it here. So this is already dimensionless. Okay? It is already dimensionless, and once every time you have a dimensionless form, in this context, you have to state assumptions on the dimensionless numbers. Okay? Numbers or set of numbers. Here we have not a dimensionless number, we have a dimensionless tensor, this A. This is the stiffness tensor, no? But it is dimensionless. And what we are assuming here is that it is of order 1 with respect to epsilon. So it is of order epsilon to the power 0. Okay. As before, we said that the viscosity, the dimensionless viscosity was of order epsilon square. Here, on the other hand, we assume this of order 1, constant with respect to epsilon. Okay. Once again, if you change the hypothesis, the formulation that you are going to obtain is different. So this is a matter of how you how your model is stated. Okay, so why I'm telling you this? Because now this is the expansion for E. No? So we have a leading order term, which is this, and then another term, which is that of lower relevance with respect to epsilon. As the A, the stiffness, is of order 1, the same behavior of the E you can find for the sigma, because sigma is A E. As E is of that form, sigma would be of that form. So you have a sigma minus 1, say a sigma of order 1 by epsilon. So sigma, you have to write sigma like that, no? Sigma is A double contraction E. So this would be A double contraction 1 by epsilon dy of u naught plus Ex of u naught plus dy of u1, etc. in the other terms. So this A times dy, I'm calling it sigma minus 1 because it is the coefficient of 1 by epsilon. The term A gradient Ex of u naught plus Ey of u1, I'm calling it sigma naught because it is the coefficient of epsilon to the power 0. And then I didn't put the other terms, but if you go further, you will have a sigma 1, which will be A of Ey of u2 plus Ex of u1, and so on. Okay. To these sigmas, you have to apply the divergence, which also been expanded into divergence x plus 1 by epsilon divergence y according to this expansion that we already introduced plenty of times. Okay. So let's try to line. So we are at this level. Let me cancel this part. So now we have the equation that we have to manipulate is divergence of sigma equals 0, which will be the divergence x of sigma plus 1 by epsilon, the divergence y of sigma, exactly as we said for the gradient. But sigma is 1 by epsilon sigma minus 1 plus sigma naught plus other terms. And so what do we have? We have 1 by epsilon divergence x of sigma minus 1 plus divergence x of sigma naught plus 1 by epsilon square divergence y of sigma minus 1 plus 1 by epsilon 1 by epsilon divergence y of sigma naught, okay, plus other terms. Okay. So the highest order term is this. It's the one of order 1 by epsilon square. There is no other term higher than that. So the problem that we have is the highest order problem is this. Is the divergence y of sigma minus 1 equals 0. Sigma minus 1 is A Ey of u naught. No? So we have the divergence y of A Ey of u naught equals 0, and the boundary condition obviously telling you that the sigma n is equal to 0, so the highest order condition will be on the sigma minus 1. So A Ey of u naught dot n equals 0. Okay, so this is what? This is a standard elasticity problem, no? On u naught, considered as a function of y, because we have the divergence of A EY of U naught. So U naught also depend on X, but exactly as before in the Stokes problem, reading this equation, we don't care at all of the dependency on X. This is a problem defined at the level of the unit cell, because there are just divergence and gradients with respect to Y, boundary conditions on gamma, periodicity on the external boundary of the problem. So what is the solution of this problem? You have a zero traction at the interface. You have zero traction at the interface, no assigned displacement. So what is the solution of this problem? For U naught or as a function of Y. Imagine that you have a body. Now your problem is this: you have your unit cell, which is your body, your solid body. No one is loaded. There are no bulk forces. There are no tractions. Okay, you are requiring periodicity, so it's not nice picture because it doesn't respect periodicity. Okay, so you have periodicity. Okay, this is not the answer, let's do it this way. Okay, you have periodicity, so imagine that this corresponds exactly to that and this exactly to that. My picture is not perfect. But zero bulk force, zero weight, zero traction, so what happens? Nothing. Just nothing. The displacement will be zero. Zero with respect to Y. Because this is a problem defined the Y variable. So the conclusion will be the same as the one that we have seen before for P naught. For P naught was simpler to see because we said we have found gradient Y of P naught equals 0, so P naught constant with respect to Y. So P naught just a function of X. So gradient Y is 0, and so P naught just a function of X. This is less obvious, but it's the same. So the U naught considered as a function of Y is 0, but indeed it is not necessary that it is 0 because we are not blocking completely the displacement. This cell can just fly on my whiteboard. No? So the solution is given. It's not completely known. It's known, but if you superpose a translation which is constant with respect to Y, but will be a function of X, it's fine. So if here you put the gradient Y of U, which is just a function of X, this E of Y disappears. No? And also here. So a constant function with respect to Y works. And so the conclusion is that the highest order problem tells us in a similar way as it was for the Stokes problem that U naught, now U naught, it was not the case for P in the Stokes problem. P naught was a function of Y. Now we have done all the calculation to find the dependency of V naught on Y. Here the U naught doesn't depend on Y obviously because the problems are not the same. So U naught doesn't depend on Y. Okay, here I'm evolving the Lax Milgram theory, but in any case it's the trivial problem. I mean, zero traction, zero bulk force, just periodic boundary conditions. The only possibility is that the displacement is constant with respect to Y. So this is the first result. The U naught is just a function of X. Now we have to go further. Clear? No? So we have just exploited this part of the problem. No? So now we have to consider the other two terms, which are these two. This and that. So the terms of order 1 by xi. This and that. Huh? Okay. So the formulation of this of the problem now is the following. You have sigma naught. You have sigma minus 1, which is sigma minus 1 was this A of gradient of EY yes, let's find so we have now to solve, before we had the divergence y of sigma 1 equals 0, now we have divergence x of sigma minus 1 plus the divergence y of sigma naught equals 0. Now, the point is that this sigma minus 1, by definition, it is A double contraction EY of U naught. But we said that U naught is just a function of x. So, this guy is 0. And so, the divergence x of 0 is 0. So, this term disappears. Because, okay, this is a divergence x, okay, but the point is that the sigma minus 1 is a EY, so a gradient y of a function which just depends on x. And so this condition kills the sigma minus 1. So what remains is the divergence y of sigma naught. And sigma naught is A gradient x of U naught plus gradient y of U1. Is this one. So the problem now reduces, so this is 0. What remains is just the divergence y of sigma naught, so A double contraction Ex of U naught plus Ey of U1 equals 0. Okay. The same for the traction condition, because the traction in principle is the sigma minus 1 plus is sigma naught, because sigma minus 1 we said that in any case is 0. So the traction is sigma naught n equals 0. So once again, Ex of U naught plus Ey of U1 equals 0. Dot n equals 0 on the boundary. So this is the differential problem that we have now to solve. Divergence y of A Ey of U1 plus A Ex of U naught equals 0 in the domain, and A Ey of U1 plus A Ex of U naught dot n equals 0. This is not a trivial problem, because exactly as in the case of Stokes' problem, where we had the parameterization of the solution for P naught in terms of gradient x of P naught, here we have to solve with respect to U1, considering our loading given by this Ex of U naught. U naught is just a function of x. Here we have divergence y, gradient y. The problem is once again a local problem defined in the unit cell, so with respect to the y variable, and this Ex of U naught now is our loading. So in the case of the Stokes problem, the loading was the macroscopic gradient of pressure. In the problem of classical elasticity, the loading for the unit cell problem is the macroscopic gradient of strain. So in fact we have, if we are in 2D for instance, how many problems, independent problems we have to state? When we have the gradient of pressure, when we have the gradient X of P naught, we said, and this it was what we did in our numerical calculation, we took either this equal to E1 or this equal to E2. Now we are replacing this with Ex of U naught. So this is a second order tensor. So if we are in 2D, how many independent problems we have to solve? This in 2D is a matrix of, what is the dimension of this matrix in 2D? 2 by 2, 2 by 2, no? But symmetric. So this means that we have to solve a unit problem with this loading, a unit problem with this loading, and a unit problem with this loading. If we are into it, no? Multiply exactly as it was here. Here we solved the problem with this loading and that loading. No? So, but this was a vector, our loading. Here the loading is a tensor. In 2D is this, in 3D, so in 2D we have to solve 3 local problems, parameterized by the XX, YY, and XY strain, macroscopic strain. If we are in 3D, we have to solve 6 local problems, because of the symmetry of E, obviously. Otherwise, if we do not have symmetry, but we have, so we can explore. Okay, so this problem is not trivial at all, exactly as it was not trivial the problem for V naught previously, because it is a divergence Y of A EY, but with this loading. So for instance, the first one would be with a unit macroscopic longitudinal strain along the X direction, then a unit macroscopic longitudinal strain along Y, and a unit shear strain XY. And this term, this loading appears both at the level of the bulk equation and also at the boundary. Okay. So this problem, obviously, exactly as it was in the Stokes problem, we not solve it by ends. Before it was trivial. We just observed the problem and we noticed that as there was no loading, the solution was the trivial one. Was not depending on y. Here we have to solve the local problem. So we have a problem defined at the level of our unit cell with periodic boundary. So what is the unknown here? Is U1. No? So in this statement, the unknown is U1. U0 is the parameterizing, the quantity parameterizing the loading, the X of U0. So we are looking for the solution of the problem in terms of U1. And this you cannot solve by ends. You have to state a weak formulation and construct a numerical implementation, as we did in the example that we have seen yesterday. Not yesterday, and last week. Okay, so the formulation is the weak formulation of the problem is this one. This is quite trivial, in fact. It's the standard. It's the standard stuff, no? Because we have the program is written like that. So this is the bulk, and this is the boundary condition. So what you have to do when you want to solve this problem, you construct the wave formulation. So what do? You multiply this by a test function. Your test function would be a test function which is related to the unknown, so a u1 hat. And we call it alpha. Okay, but I mean the meaning is so you have to multiply this by, here I call it alpha, so let's use the same alpha y, by the test function, by the test, the vectorial test function alpha y. It's a vectorial test function. Because this is a vectorial equation, divergence of a tensor, which is a vector. So you put an alpha there, and then you play with integration by parts. So the divergence, you have the usual formulation. So you have in the bulk you have the A times the argument of the A multiplied by the symmetric part of the gradient of alpha, and then you will have, not because in fact you are writing this, divergence of sigma, this was sigma naught, you are writing this. Okay. So you are writing this. So this you apply, this is divergence y. So you just apply the divergence theorem, this becomes sigma naught double contraction gradient y of alpha y plus on the boundary of omega s sigma naught n alpha y. Okay.
This is what the bulk becomes?
This is the weak formulation of that, multiplied by half, and then integrating by parts, it gives you that. But this term, once again, disappears. Why? Because on the internal part of the boundary, this is zero, traction is zero, and wherever you have, wherever you are at the boundary of your domain, as you have periodicity, obviously also the alpha should be periodic. So you have sigma naught and alpha which are periodic, n is anti-periodic, and so when you sum, this contribution disappears, and so what remains is this. So this is the weak form. Okay. So the weak form of the problem is that in the unknown u1 and the loading u0 gradient x ex of u0. Okay. So exactly as before, now obviously in principle we should implement a tool for solving the problem having a certain geometry of our unit cell. But in any case, independently of the specific solution, what would happen is that once again this is a linear problem. as it is a linear problem, our solution U1 will be a linear combination of the loading, which is Ex of U0. No? So U1, the solution, U1 of Y, of X and Y, will be a linear combination of Ex of U0. Huh? Exactly as before, the P0 was a linear combination of the gradient X of P0. And we call, so this is the way in which we are writing the expression. This linear combination is written like that. It's not so nice, but because obviously the Ex is a tensor, so it has two indices, Ex Lm of U0, this is our loading. U is a vector, no? U1 is a vector, so the result would be that UI1, so the ith component of U1, will be a psi I Lm of E times Ex Lm of U0. So I'm just writing this. U1 is equal to psi Ex of U0. Obviously, I should clarify that this is a vector field. This is a second order tensor, and so in the middle there is a third order tensor, where I saturate two indices here to get the vector. Just a matter of indices. So this psi, in fact, is the solution, this psi I, Lm, will be the solution due to, for instance, Ex of U0 equal to 1, 0, 0, 0. Okay. So the psi, for instance, the psi 1, the psi 1, 1, the psi 1, 1 would be the solution of solution of the problem for U1 when epsilon xx is equal to 1, epsilon xy equal to epsilon yy equal 0. Epsilon e, sorry. We call it e. Okay. So I'm isolating just the contribution coming from the xx11 component. Y2 the same, but with now exy equal to 1 and the other two equal to 0. And xi22, the last one. Xi21 obviously will be the same as xi12. So the solution for U1 will be given by this solution of the problem for unit strain, the psi, times the strain. We have to add, in this case, to this solution, so this, in fact, yes, we have to add to this solution also an additional contribution which purely depends on x. Why? Because the point is that according to the structure of the problem coming from classical elasticity, as we are not prescribing, we are not fixing the displacement of every point of our unit cell. No? This unit cell is floating. So in fact, the solution is known by a constant with respect to y, which means by a function of x. And so the solution should be written like that but you will see that this object will be incorporated later in U naught, so we don't care too much. The main point is this. Okay. So disk size I, sorry, disk size LM psi, the I is just the index due to the fact that we are considering the I component of the displacement. Disk psi LM plays exactly the same role as in the case of the Darcy equation. We wrote the Wj, not the velocity, due to the gradient of pressure, the unit gradient of pressure along the j direction. This is the displacement due to the unit strain along the LM direction. So 1, 1, 1, 2, 2, 2, and so on, if we are in 3D. Okay. But this is obviously not the only result, because this gives us the local solution. So that for the moment, what we have obtained is that U naught is a function of x, is just a U naught of x, and U1 is a U1 of x and y, okay, which is given in terms of the x of U naught plus this U1 bar of x. So now, what can we do? We can go back. No, we cannot go back. We have to go further. Yes, because I didn't write explicitly because I stopped at the let me see. Yes, because I stopped to the problem written for sigma minus 1 and sigma naught. No? The problem that we have solved here was this. I wrote before, but now I cancelled. It was this. It was divergence x of sigma minus 1 plus divergence y of sigma naught equals 0. No? This we wrote. Then I said that there are other terms in the cascade of coordinates. So after this, there is that divergence x of sigma naught plus divergence y of sigma 1, because you scale term by term. So we are not trying to solve this problem, but we just exploit it.
Sorry, can you read a couple things on the board? Going back, multiply by the what for function of alpha 1?
Here.
All the way on the other side. Multiply by
Here.
Sorry.
Here, multiplied by a vectorial test function alpha 1.
Vectorial test function.
Vectorial because it's obviously it's a displacement.
And then you say this top line, U1 xy will be a linear combination of
X of U naught.
EX.
Yes. It's exactly the same story as in the previous equation, where we wrote that that the velocity, was a linear combination of the components of gradient x of P naught. So the EX of U naught plays the same role as the gradient x of U naught before. Okay? So now, so here we are for the moment. I took this equation just together with its boundary condition, sigma 1 and equal 0, because I want to exploit it to get the macroscopic equations of our problem. So if we take this and as we did before for the divergence of the velocity, if you remember, no? So I can calculate the average over omega s of that equation, divergence x of sigma naught plus divergence y of sigma y sigma the divergence y of sigma 1 equals 0. Okay. This is together with the boundary condition sigma 1 and 0. So when you calculate this average, what do you get? You get exactly, you can do the same, this is obviously an integral over dpy, no? This is an omega sy, the integral is with respect to the y value. So the first term can be rewritten like that, divergence x of integral over omega s of sigma naught dpy plus, and this goes to the boundary, obviously, sigma 1n equals 0. But this guy, as we said plenty of times, is 0, because on the internal boundary, if there are traction, is 0, and on the external boundary, we have periodicity of sigma 1, anti-periodicity of n, so when you sum up, you get 0. So the conclusion is that you have this macroscopic equation. So you call, you have this result, this disappears. What remains is this divergence x of this average of sigma naught equals 0. You call this the sigma, the macroscopic stress. Okay, these brackets mean average. Okay, and this sigma naught is what? Is a of e y of u1 plus ex of u naught. Huh? Okay, this is sigma naught. But we are calculating the average of this. And we know that u1 is that. Is a function of u naught. Okay? So when you calculate the EY of u1, this guy obviously doesn't play any role. This is a function of, this is the only function of y, the psi, because the psi is the solution of the problem on the cell. And so the conclusion is that the conclusion is that the average sigma, the macroscopic sigma, or call it with the bracket as you prefer, let's call it sigma n. This is 1 by omega, obviously, and then I will put also the 1 by omega. It doesn't change anything for the divergence. But 1 by omega of omega s of what? Of A, and now this EY of U1 is an EY of psi how to it's EY of let me write it yes, let me write it like this of Ex of u naught. Okay, this double contraction is what is indicated over there, plus Ex of u naught. So you see what is happening. This is a linear function of Ex of u naught, and the dependency on y is here, inside. So this is an horrible way of writing things, so it's not nice at all, but you see what I mean. So this is the average of sigma naught is the AIJKH, A. Double saturation with the index KH kh of u1 and ex kh of u0. But this guy u1 is the ey of u1 is the ey of psi ex of u0. So in the end, you can rewrite all this stuff as a C double contraction to with Ex of u0, because Ex of u0 can come out from the integral. So this C is the macroscopic stiffness, because it is the quantity related to the macroscopic stress with the macroscopic strain. And you have explicitly the definition of this C. And this C is not the A. The A was the stiffness at the microscopic level, but the C is the average of this microscopic stiffness plus the same quantity but multiplied by the Ey of psi. So here there is the solution of the microscopic problem. Exactly as in the case of the Stokes problem, the permeability was an average of the velocity of the velocity of the solution for velocity at the microscopic scale. Here the stiffness is involving the solution for the displacement at the microscopic scale. Okay. So we got two results. We got that the macroscopic equation is divergence of sigma of divergence x of the average of sigma naught equals 0. So the average of sigma naught is the macroscopic stress, and this macroscopic stress has a constitutive relation between sigma naught and E of x u naught, so the symmetric part of the gradient of u naught, the usual, given by this C, which has this form. So in this form, we have incorporated the fact that our solid is not our medium is not a solid medium, but it is a porous medium with empty space. Okay? And so this is the result. Obviously, indeed, we should not write the divergence x of sigma dot equals 0, but because there are some other terms that we can put inside. No? If we decide to neglect the terms of order epsilon, we get the usual equation, macroscopic divergence of sigma equals 0 because there are no ground forces, and the constitutive relation, the average of sigma dot equal to C Ex of u. Purely macroscopic. Okay, so we got the linear elastic constitutive relation at the macroscopic level, starting from the linear elastic constitutive relation at the microscopic level, but obviously the C is not the A. The C is the macroscopic one, the A is the microscopic one, and the C depends on the solution of the unit of the problem on the unit cell, exactly as it was before for the permeability. Okay. So the last step that we will do tomorrow, and we will conclude, will be to mix the two results that we got today and that we got before for the Stokes problem, in order to consider a porous skeleton field saturated by a fluid, where the fluid can flow through the porous skeleton. So we have to mix up the two problems, the one for the displacement that we have discussed today, the other one for the velocity and pressure that we discussed previously, considering, as we were suggesting at the beginning, the interaction at the boundary between the two constituents via the pressure of the fluid. Okay, and from there we will recover the bio-constitutive relation, and there will be some nice surprise with respect to the standard formulation that we can discuss tomorrow. Okay, so try to think of this in such a way that if you have questions, we can come back on a few points tomorrow after.
Professor,
Yeah, please.
what have you written for psi? the bracket.
Where?
Yeah, there.
The xi?
Yeah.
Yes, the xi is this. Is, well, I wrote the solution for u1 as a function psi I, which is the third order tensor, times dx of u0. Okay. So in fact, this psi I, as I was telling you before, plays the same role as it was the wj for the velocity. Now for the velocity we wrote this. We wrote pi equal to wj I p naught comma j. So the I component of the velocity is the I component of this wj, which is the velocity relative to a unit gradient of pressure along the j direction multiplied by the gradient of the naught along the j direction, summation with respect to j. Here it's a little bit more complicated because the loading is not a vector, but it's a tensor. And so the object that it is in the middle is a third order tensor because it eats a tensor and gives you a vector. Okay.
This part,
Okay.
the end, but at the
Just
end,
really quickly, not my way,
I
right?
think
We
this
had
is 0, not
the unknown and you not being the loader. Is it just always written in terms of x and y here? Where did you not x come from? Like what you wrote in red, going from the first step to
Here,
down, and then
no, I just indicated that you know is we solved the previous problem for the naught and we observed that you know is just a function of x.
And U1 as our unknown is written in terms of x and y, but we know that it's not going to rely on.
Yeah.
Okay, so we know it's not going to rely on y. It's going to
Why I should expect that? The point is that at the beginning I assumed that all the fields depend on x and y. Then I can discover that some of them only depend on x. But a priori I cannot know.
You're just establishing here again that we have it in terms of it's uy in terms of x and y.
Yeah.
Okay.
So I discovered that the u1 is a function of y. In fact, a priori there is no reason for considering that the function doesn't depend on y. In the particular case of u0, as the problem is the trivial one, it's just 0.
Yeah, it's so much trouble.
I'm really confused because sometimes you're using
Superscript something.
Sorry.
So which
No,
one?
it's no. Just because I have not sufficient room,
I was just
so
about
this is a
Oh,
equal,
okay.
it's a function of y.
Oh,
So, superscript and subscript, it's the same. It's exactly the same. So this one is yes, 0.
And this is microscope.
Macroscope, microscope, big and macroscope.
oh, that's macroscopic. Big M. Yes.
In any case, you find better to look at what I wrote in the slides because it's more consolidated version, even if there is some mistakes. Because sigma minus 1, we observed was specified as a gradient y of, in fact, it was an ey of u0. Okay, but ey means gradient y, and u0 is just a function of x. So no, same y. I said that.
Oh, there's my question again.
Oh, side dependent on y, not side.
I was speaking and there was not so much room. I put it down.
And then it's the EX of 1.
This is y of this was y. So this is an ey of u1 plus dx of u0 because of the form of sigma naught. Sigma naught was defined like that. Was this was zero.
Where does E come from?
Where did the C come from?
Big
It's
C.
No, C, that you boxed at the bottom.
Ah, the C.
Yeah.
The C is all the stuff. In fact, look at it's better to look at this version because it's more clear. So you see that you are calculating the average. This is what is written there. That integral is this. Okay. Now you see that the dependency on Ex of U naught is linear, and the X of U naught is constant with respect to these brackets, which indicates the integral with respect to Y. So you can extract this from the integral, the X of U naught. What remains is the integral of something which I call C. And what is the C is this? Is the integral of the A plus the A times the Y of psi. With the good indices placed correctly. Okay, so the point is that this object, which is the macroscopic stiffness, depends on the microscopic stiffness, but not just on it, but also on the solution of the unit cell problem, because this is a EY of psi. So this is the symmetric part of the gradient y of the solutions relative to the unit problems. Okay.
Could you just repeat what you just said? Symmetric part of? Sorry. Symmetric part of what you just
Symmetric
said?
part
Could you just repeat what you just said?
of
Sorry.
It depends on the solution to the unit cell problem.
symmetric part symmetric part of the gradient of U1. No? So this EY is the symmetric part of the gradient y. Exactly. Okay. No, I guess. Very good.
What is this symbol? Why is there a line?
This is just the